Today on How It's Made. Brushes and push brooms. Our sweeping report will leave you bristling with excitement. Blackboards, a topic chock full of fascinating facts. Smoked salmon, the whole process, locks, stock, and bagel. And zippers, we're off to a factory that pulls it all together. Nothing scrubs or sweeps quite like a good sturdy brush. Cleaning brushes in North America date back to about the 1830s. Their bristles were usually made of wire twisted into wood. Today we have many different bristle materials, both natural and synthetic. The first factory manufactures the brush block, the hardwood base that holds the bristles. It's usually made of maple, but sometimes oak or beech. After cutting the planks to the required width, they use a special wax crayon to mark lines on both sides of any cracks or knots in the wood. A laser then reads the marks, guiding a saw to cut out the faults. At the same time, the saw chops the planks into block-size lengths. The next step is called molding. A series of saws trims the blocks to the required thickness. Now they contour the pieces using a machine appropriately called a shaper. The machine revolves, running the block's outside edge against a cutting head. This profiles half the block. Workers then turn it around and line it up for a second pass to profile the other half. There's a different shaper machine for each model. This type is known as a dauber, a brush for waxing shoes. For the cuts to be accurate and smooth, it's essential that the machine's cutting heads remain sharp despite repeated use. That's why they're made of carbide, a material more resistant than steel. Workers run certain models against an extra cutting head to carve a groove in the block's edges. The groove gives your hand a better grip on the brush. These 6.5 by 60 centimeter blocks will become push brooms, those wide rectangular brooms janitors use to sweep floors. The blocks go on an automated machine that drills a hole through the middle and carves 2 grooves in the underside. These are for the steel adapter that'll hold the broom's wooden handle. Rounded push brooms sweep more easily in corners. To produce those, workers just take the rectangular push broom blocks and round the corners against a cutting head. At another factory, the blocks go onto a machine that pierces holes for the bristles using a computer-guided drill. This particular model, a push broom, needs 240 holes. It takes barely a minute to drill them all. Next, the blocks go on to the bristle installation machine. Bristles can be made of horsehair, vinyl, plants or tree leaves, or synthetics such as polypropylene. The bristle installation machine is fully automated. As we see here in slow motion, it takes about 40 strands at a time, folds them in half, then inserts and staples them into a hole. Here's what that bristling action looks like at actual speed. The machine fills 4 holes per second. The factory uses this same process regardless of the style of brush block or type of bristle. Computer software guides the machinery to follow the correct pattern, making possible a sweeping array of brushes and brooms. Chalk one up for the blackboard. This trusted teaching tool goes back centuries, yet still remains the focal point of the classroom. Today's blackboard, or chalkboard as it's also called, hasn't changed that much in appearance, but the materials used to make it have changed. Our lesson begins at the blackboard factory with thin sheets of galvanized steel that will eventually form the front and back surfaces of the blackboard. They arrive at the factory already pre-cut to standard sizes, 6, 8, 10, or 12 feet. First stop is a machine that blasts the sheets with acid. This removes any dirt that would prevent paint from adhering to the surface. As the sheets exit the cleaner, powerful fans dry them off. The paint is a type of acrylic enamel designed especially for blackboards. The factory adds a powdered mineral formulation to make it dry to a rougher texture. This helps chalk adhere better. Traditional slate blackboards were naturally black. Today's steel surface boards come in several colors. The most popular, though, are black and green. Some companies use colored porcelain instead of paint. Here, spray guns apply 3 coats of paint, one after another, with no drying time in between. For the paint to harden properly, it has to be heat set, so the sheets go into an oven at 218 degrees Celsius for 10 minutes. A strong fan cools them off as they exit the oven. Next, a worker sprays contact cement on the backs of 2 painted sheets. One sheet will form the front of the board, the other the back. Sandwiched in between will be what's known as the blackboard's core. It can be made of materials such as particle board, or, as we see here, 12mm thick fiberboard. Workers feed the 3 assembled layers through a high-pressure roller. It forces out any trapped air and bonds the layers tightly. They make the blackboard's frame out of one long strip of aluminum molding. It has a stain-proof satin finish. They make a series of 45-degree angle cuts. This enables them to bend the strip around the board's perimeter, creating neat corner seams. Workers file down and polish any sharp edges left by the cutting. After verifying that it's perfectly square, they fasten the frame using either rivets or screws, depending on the model. Then they attach an aluminum rail along the bottom to hold the chalk and eraser brushes. This model happens to be a reversible mobile blackboard, the type typically rolled into conference rooms. It has a couple of extra components: a pivot mechanism, enabling the board to be flipped to the other side, and a latch system for tilting the board to different angles. The blackboard stand is made of painted steel tubing. It rolls on rubber and chrome-plated steel casters. The factory takes samples from the production line and subjects them to rigorous quality control testing. These tests ensure that the painted surface is glare-free and can withstand everything from chemical solvents and extreme humidity to heavy impact and hard scratches. The company has even designed this special machine to conduct a killer durability test. It applies 100,000 chalk and brush strokes using the typical amount of pressure a person would use. For the production batch to score an A and make it to market, surface wear on the sample has to amount to less than 1/100th of a millimeter. And that's not all. The paint finish must still be matte. A writing test has to produce chalk lines that are clear and dark enough, and the writing has to erase cleanly and easily. For thousands of years, smoked fish was a survival food. People would cure their catches by salting them and hanging them to dry, or by smoking them over an open fire. This enabled people in cold climates to stockpile nutrient-rich fish for those long winter months. Today we smoke fish primarily to enhance its flavor. This is wild sockeye salmon that was gutted and frozen right on board the fishing trawler to preserve maximum freshness. The smokehouse defrosts the fish over 15 hours in running water that's just 2 degrees above freezing. This slow, cold water thaw helps prevent bacteria from forming. Next stop, filleting. First, they slice off what's known as the collar, the fish version of the neck. Then they cut each fish in half lengthwise, separating 2 fillets from what's called the control bone, the fish equivalent of a spinal column. The tail is attached to it. They feed the control bones into a machine that strips off any remaining scraps of flesh. The machine grinds these bits into minced salmon, which is used to make salmon pie. They trim the fillets using a razor-sharp knife, slicing off the fins, any excess fat, and any control bone fragments left behind. After this, the fish will be ready for curing, a preservation process that also enhances taste. Workers coat the fillets in a mixture of salt and 26 spices, then let them sit for roughly an hour and a half. This short cure time will limit the salmon's salt content to less than 1%. To stop the curing process, they rinse off the coating with cold water, then glaze the fillets with maple syrup to neutralize any remaining salt residue. Some companies use a less costly mix of boiled water and brown sugar. The fillets go into a huge smoke oven. Workers load its combustion chamber with sawdust. Maple tree sawdust for the first 8 hours of smoking, cherry tree sawdust for the next 8 hours, and apple tree sawdust for the last 8 hours. This particular sequence is a major factor in flavoring the fish. They douse the fire with water to generate smoke. This process is called cold smoking because the oven temperature is 10 degrees Celsius, significantly lower than the industry norm of 25 degrees. Smoking at this lower temperature takes at least 24 hours, 3 times longer than the norm. But the company says it produces a moister product. When the fillets come out of the smoke oven, they're thoroughly cooked, but still have the consistency of raw fish. Workers remove the pin bones, 40 thin bones per fillet, located between the head and fin. The fillets then go through a skinning machine, which neatly slices off the skin without removing any flesh. Then it's into a freezer at -3 degrees Celsius. This firms up the fillets, making them easier to slice. The manual slicing machines cut them into pieces about 2 millimeters thick. Workers weigh out the amount they're packaging, in this case 70 grams. They place each portion on a tray made of aluminum-coated cardboard. Aluminum blocks the fat from seeping through. To kill off any remaining bacteria, they vacuum pack the wrappers, then deep freeze them for about an hour at minus 35 degrees Celsius. They store and ship at a milder minus 18, the temperature of your home freezer, where this preservative-free smoked salmon stays fresh for a full year. Zippers can be found on clothing, on bags, even on footwear. The zipper started out as a newfangled closure mechanism for boots and tobacco pouches. The fashion industry didn't put them on clothing until the 1930s, some 80 years after the invention of this fabulous fastener. An American, Elias Howe, was the first to patent a zipper-like clothing fastener in 1851, but he never ended up marketing it. It wasn't until 1893 that another American, Whitcomb Judson, designed a similar device called a clasp locker. He eventually hired a Canadian engineer, Gideon Sundback, to simplify the original complex design, which had never really taken off. In 1917, Judson and Sundback patented the modern zipper. Zipper teeth are made of either metal, plastic, or nylon. The fabric part of the zipper is called the tape. It's usually polyester, but sometimes cotton or a fireproof fabric. To make metal zippers, the factory feeds a long continuous roll of tape into what's called the teeth machine, along with a long roll of metal ribbon known as flat wire. As we see here in slow motion, the machine cuts off a tiny piece of flat wire, forces it through a die that forms it into a tooth shape, then clamps it onto the edge of one side of the tape. The machine does all this at a rate of 45 teeth per second. These zipper teeth are aluminum. Sturdier zippers are made of stronger metals, such as brass and nickel. Depending on the model, teeth can range in width from about 3 to 10 millimeters. The wider the teeth, the thicker they have to be. Workers now feed two tapes with metal teeth into what's called the joining machine. The teeth interlock, meshing the two halves of what's now a continuous zipper. From there, it's into a cleaning machine, which first washes the zipper, removing any shards of metal left behind by the tooth-cutting process. After drying the zipper, the machine applies a coat of hot wax. This lubricates the teeth so the slider will glide over them smoothly. Next stop is the gapping machine. It removes a 4-centimeter long section of teeth at regular intervals. They'll later cut the tape at these gaps, dividing the continuous zipper into several shorter zippers. There are two main types of zippers. Closed-end zippers are the kind whose two halves don't separate at the bottom when opened. Purse zippers, for example. These need a part called a bottom stop, a thick piece of flat wire positioned at the base of the zipper. When you unzip, it stops the slider and prevents the two halves from separating. Open-end zippers are the kind whose two halves do separate at the bottom when opened. Jacket zippers, for instance. At the bottom of these zippers, a machine applies a clear reinforcement strip. This stiffens the tape so that the next machine can apply the pin and box. The pin is that vertical piece of metal on one half of the zipper that you have to align in the box on the other half before you can pull the slider to zip up. The next machine installs the slider. Watch in slow motion as it opens each gap and hooks a slider onto the track of teeth. The next machine inserts what's called the top stop, a thick piece of flat wire that stops the slider at the top of the track when you zip up all the way. The machine then slices the tape at each gap, separating the finished zippers. Plastic zippers are made quite differently than metal ones. The tape is the same, but the teeth are made from plastic pellets. A machine melts them, then injects the liquid plastic into a mold that's the shape of a strip of zipper teeth. The mold cools almost instantly, hardening the plastic. The machine then stamps the teeth onto the tape, automatically gapping the desired zipper length at the same time. The excess plastic in the middle is remelted. There's no joining machine to mesh the two halves of plastic zippers. Workers do this manually so that they can inspect the plastic teeth to make sure they're well formed. Then automated machines install the remaining components. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net. The How It's Made crew vehicle is courtesy of Subaru Canada.